right, hello everyone. We are going to do our very last section today. It is section 5.2. This one's focusing on area, specifically area instead of between a function curve and the x-axis. We're focusing on area between curves. So let's begin. And let's begin with a little bit of review. You might recall that if I want to find this area, say I'm given some function f, looks something like that, and I take some interval, say from a to b, and if I want to find the area of that region, maybe let's just call the area A. The area of that region we'll call A. Then the area of that region I can use a definite integral to find. I know it's equal to the integral from A to B of that function f of x dx. Or in words I could say this is the area bounded by the function f and the x-axis, and the x-axis over the interval from a to b. A definite integral such as this gives me the value of that area. Alright, so we know that from material we've already gone over. Let's change up the region a little bit. Let's say instead of that region, let's look at this region. Let's see here. Let me actually make that a little bit smaller so I have a little more room to work with. Let's say this is A. Let's say this is B. Let's maybe draw a couple of simple regions. Let's let that function, let's call it g of x. Let's call it y equals g of x. I'm going to draw another function, maybe in green. Let's call that function f of x. Y equals f of x. Okay. And I want to find the area of this region that is enclosed by those two functions. Okay? Maybe I'll call that region A. Or the area of that region I'll call A, I should say. Let's make a little observation that those two intersect at A and B. How could we use our knowledge of the definite integral to find the area of A? Let's observe something that, let's see, if I just wrote integral from a to b of, say, f of x dx, which is that green line, then the area that we would be finding when we calculated that definite integral would be this area from a to b. Oops. To b. What's this region underneath the graph of the function f of x? Oops. Keep hitting the wrong tool. So we would find this. Okay. Maybe I'll call that region A1. And I'm just going to go ahead and draw the graph of g of x on top of that so we have it. It looks something like that. Now, the integral from a to b of g of x dx, what does that integral indicate? Draw the graph again. Let's see here. I'll draw the graph of g of x like that. And let's see, if this is a, if this is b, then the integral from a to b indicates that I am finding the area underneath. I'm actually going to bring my graph down just a little so it looks more like the one on the left. There we go. So the integral from a to b of g of x dx gives me this area. Maybe I'll call that A2. And I'll go ahead and draw the graph of f on top of it. Right, looks like that. Okay. It looks to me like this region here is this entire region less this region. So if I take away this region, which is the same as this region, from whatever this integral gives me, then it appears that I would have this little region here. So I might say that the area A is equal to, well, it's equal to area 1 minus area 2. Well, area 1 I get by taking the definite integral from a to b of f of x. Area 2 I get by taking the definite integral from a to b of g of x. What if I subtract that right-hand integral from the left-hand integral? So I might say that, again, on the right-hand side, this is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx, which I could combine. I have a rule of integration that allows me to rewrite a sum or difference in the integrand as two different integrals. I can go backwards, do the same thing, because you notice that these bounds are the same on both functions. So this is equal to the integral from a to b of f of x minus g of x dx. So that would be how I could find the area of that region that is bounded by two curves, as is shown here. Maybe let's state that formally. There we go. The area A of a region bounded by the curves y equals f of x and y equals g of x, which we noted previously, and the lines x equals a and x equals b. In other words, this is bounded from a to b, where two things occur. First of all, f and g are continuous functions, which the two that I drew are certainly continuous, or were certainly continuous. And then we also have this feature that f of g is greater than or equal, or f of x, excuse me, is greater than or equal to g of x for all x on that interval from a to b. So what I might picture in my mind when I think about this is f would be what we might call the top function. So it lies above the area that we are trying to find. And g we might call the bottom function. So it lies below the area that we are trying to find. And so the y values for the function f are greater than the y values for the function g of x for all x in this interval. So if I have that criteria in place, then the area A is equal to the integral from a to b of the function f of x minus the function g of x dx. So I can subtract bottom function from the top function, find the interval from a to b, because the function is bounded from a to b, and I get the region between two curves. Let's do another example of that. Let's do this example. Let's find the area. Find the area. The area between curves y equals x plus 5 and y equals x squared plus 1 on the interval from 0 to 2. So on the interval from 0 to 2, another way that I could think about this is the area is bounded between y equals 5 and y equals x squared plus 1 and x equals 0 and x equals 2. That's also a way that this might be stated. So the first step in any of these is I need to know on this interval from 0 to 2, or between x equals 0 and x equals 2, does one of these functions consistently come out above the other function? So I need to draw this. If I graph those functions, I'm only considering this from 0 to 2. So I'm not going to go to the left of the y-axis. I know that the graph of y equals x plus 5 is the graph of a line. Has a y-intercept at 5. It has a slope of 1 over 1. Okay. So it looks something like this. Okay. And the graph of y equals x squared plus 1 is a parabola. And it is the parabola x squared that has been shifted up by 1. So it has a vertex there, point at 1, 1, or 1, 2 rather. Does the same thing on the other side. But if I am trying to find the region between that on the interval 0 to 2, so that's from x equals 0, which is right here, to x equals 2. So this is 1, 2. Let me draw the axes in black. Then the region that I'm looking for is right here. The area between these two curves and between, oops, I drew too much region, didn't I? There we go. Between x equals 0 and x equals 2. So, there we go. That's the region in question. Okay. Now, for that region, I can definitely state which function is on top and which function is on bottom. This is the graph of my line f. This is the graph of my line, or of my parabola g. It looks like f is on top. So So I'm going to call this the top function. I'm going to call this the bottom function. Okay? And the area that I am trying to find can be calculated by taking the integral from, let's see, my leftmost x bound is 0 to x equals 2 of that top function, which is x plus 5, minus the bottom function, which is x squared plus 1 dx. Okay, so I have my integral set up. Now I can apply my rules of integration, of calculating the definite integral using the fundamental theorem of calculus to find the value of this. So this is the integral from 0 to 2. I'm going to simplify the algebra a little first. I have a negative x squared plus x. 5 minus 1 is plus 4 dx. Okay, integrate that. The antiderivative is a negative x cubed times 1/3 plus x squared times 1/2 plus 4x, and I'm evaluating that from 0 to 2, which is negative 1/3 times 2 cubed minus, or plus rather, 1/2 times 2 squared plus 4 times 2, and then f of 0 is 0, so I could say minus 0 is equal to 22/3. So 22/3 is the area of this particular region bounded by those two curves. And I think we will pause there and carry on in another video.